Have you ever heard a loud boom in the sky and wondered what it was? That mysterious sound is known as a sonic boom. That was likely a sonic boom, created by an object traveling faster than the speed of sound. This speed, called supersonic speed, is a fascinating area of science and engineering. It pushes the boundaries of what we know about flight and physics. Supersonic speed is defined as any speed that exceeds the speed of sound. We measure this speed in Mach numbers, a term named after the physicist Ernst Mach. Mach 1 is equal to the speed of sound, which is about 768 miles per hour at sea level. This speed can vary slightly depending on factors like air temperature and altitude. For instance, colder air can make sound travel slower. Objects traveling faster than Mach 1 are considered supersonic. The quest to break the sound barrier, reaching Mach 1, captivated scientists and engineers for decades. In 1947, Chuck Yeager achieved this milestone in the experimental Bell X-1 aircraft. This breakthrough ushered in the era of supersonic flight, changing aviation forever. Today, supersonic speeds are not limited to experimental aircraft. Fighter jets, missiles, and even spacecraft routinely travel faster than the speed of sound. Understanding the science behind supersonic speed is crucial for developing these advanced technologies. It allows us to innovate and push the limits of what is possible in aviation and beyond.
Designing aircraft for supersonic flight presents unique challenges that require innovative solutions and advanced engineering techniques. The aerodynamics of supersonic flight differ significantly from those at subsonic speeds, necessitating a different approach to design and testing. Careful consideration must be given to the shape and structure of the aircraft to overcome these challenges and ensure optimal performance. One crucial aspect is reducing drag, the force that opposes an aircraft's motion through the air, which can significantly impact fuel efficiency and speed. Supersonic aircraft feature sleek, aerodynamic designs to minimize drag and enhance their ability to cut through the air smoothly. This often involves a long and slender fuselage, reducing the surface area that encounters air resistance, thereby improving overall efficiency. Another important design element is the use of swept-back wings, which are essential for maintaining stability at high speeds. Unlike the straight wings of most subsonic aircraft, swept-back wings are angled backward to reduce drag and improve aerodynamic efficiency. This design helps to delay the formation of shock waves, which are created as the aircraft approaches the speed of sound, reducing the impact on the aircraft's structure. The nose of a supersonic aircraft also plays a critical role in its performance, influencing how air flows around the aircraft. The sharp, pointed nose of these aircraft helps to reduce the impact of shock waves, allowing for smoother and faster travel. These shock waves form as air compresses around the aircraft at supersonic speeds, presenting a unique set of challenges that engineers must address.
Achieving and maintaining supersonic speeds require immensely powerful engines. These engines must generate enough thrust to overcome the increased drag encountered at these high speeds. Traditional jet engines, while powerful, often need an extra boost. This boost comes from a component called an afterburner. The afterburner is a combustion chamber added to the back of a jet engine. It injects extra fuel into the engine's exhaust, igniting it and providing a significant increase in thrust. Afterburners are crucial for supersonic aircraft during takeoff and when accelerating to supersonic speeds. They provide the necessary power to overcome the drag that increases dramatically as an aircraft approaches and surpasses the speed of sound. However, afterburners are not very fuel efficient. They consume a large amount of fuel in a short period. Therefore, they are typically used sparingly and only when absolutely necessary.
Missiles, designed for both defense and offense, also utilize supersonic speeds to enhance their effectiveness. There are two main categories of missiles: cruise missiles and ballistic missiles, each with its own unique characteristics. Cruise missiles are powered throughout their flight and typically travel at lower altitudes. They can be subsonic, supersonic, or even hypersonic in some cases. The BrahMos missile, for example, is a supersonic cruise missile capable of reaching speeds of Mach 2 to 3. Ballistic missiles, on the other hand, follow a ballistic trajectory. They are powered only during the initial ascent phase of their flight. After reaching a high altitude, they follow a parabolic path determined by gravity. While not powered for most of their flight, ballistic missiles achieve incredible speeds. Intercontinental ballistic missiles, or ICBMs for instance, can reach hypersonic speeds of up to Mach 20 during their re-entry into the Earth's atmosphere.
Section 5. The sonic boom, a thunderous consequence. One of the most dramatic effects of supersonic flight is the sonic boom, a phenomenon that has fascinated scientists and aviation enthusiasts alike. This thunderous sound, often described as a loud clap or boom, occurs when an object travels faster than the speed of sound, creating a powerful auditory experience. The sonic boom is not a single event that happens when an object breaks the sound barrier. It is much more complex. Instead, it is a continuous phenomenon that occurs as long as the object is traveling at supersonic speeds, creating a persistent and powerful sound. As an object moves through the air, it creates pressure waves in front of and behind it, altering the air's natural state. At supersonic speeds, these pressure waves cannot propagate ahead of the object, leading to a buildup of energy. Instead, they combine to form a shock wave, a cone-shaped disturbance in the air that is both visually and audibly striking. This shock wave carries a significant amount of energy, which is released as a sonic boom. When it reaches the ground, we perceive it as a sonic boom, a sound that can be startling and awe-inspiring. The strength of the sonic boom depends on the object's size, shape, and altitude, as well as atmospheric conditions.
Section 6. Hypersonic technology pushing the boundaries. While supersonic speeds have revolutionized air travel and defense, scientists and engineers are constantly pushing the boundaries of speed. This has led to the development of hypersonic technology. Hypersonic speed is defined as any speed above Mach 5, or 5 times the speed of sound. This is significantly faster than supersonic speeds and presents even greater technological challenges. Developing vehicles capable of hypersonic speeds requires overcoming extreme heat and pressure. At these speeds, friction with the air generates intense heat, demanding advanced materials and cooling systems. Hypersonic technology has numerous potential applications. In the realm of defense, hypersonic missiles could provide faster response times and greater maneuverability, making them difficult to intercept. Hypersonic aircraft could potentially revolutionize air travel, drastically reducing flight times for long-distance journeys. Imagine flying from New York to London in under an hour.
Section 7. Materials and thermal management at hypersonic speeds. One of the biggest challenges in hypersonic flight is managing the extreme heat generated by friction with the air. At hypersonic speeds, temperatures can reach thousands of degrees Celsius, hot enough to melt even the most robust metals. To withstand these extreme temperatures, scientists and engineers are developing new materials and innovative thermal management systems. These materials need to be not only heat-resistant but also lightweight and strong enough to handle the stresses of hypersonic flight. Ceramic composites are one promising material for hypersonic applications. These materials are incredibly durable and can withstand extremely high temperatures. However, they can be brittle, so researchers are working on improving their toughness and flexibility. Another area of active research is the development of advanced cooling systems. These systems could involve circulating coolants through the vehicle's structure or using a blade of materials that absorb heat as they vaporize.
Section 8. Applications and implications of hypersonic technology. The development of hypersonic technology has far-reaching implications for various sectors, including defense, aerospace, and even space exploration. In the defense sector, hypersonic missiles are becoming increasingly important. Their high speed and maneuverability make them incredibly difficult to intercept, potentially giving countries a significant military advantage. Hypersonic technology is also poised to revolutionize air travel. Hypersonic passenger aircraft could drastically reduce travel times for long-distance flights, connecting continents in a matter of hours. Imagine having breakfast in London and lunch in Tokyo. Beyond Earth, hypersonic technology could play a crucial role in space exploration. Hypersonic spacecraft could potentially reduce the time and cost of space travel, making missions to Mars and beyond more feasible.
Section 9. Conclusion: the future of supersonic and hypersonic flight. From breaking the sound barrier to developing hypersonic vehicles, the quest for speed has driven incredible technological advancements. Supersonic and hypersonic technologies have opened up new possibilities in aviation, defense, and space exploration. As research and development continue, we can expect to see even more innovative applications of these technologies. Hypersonic passenger aircraft, once a futuristic concept, could become a reality, shrinking our world and connecting us in ways we never thought possible. The future of flight is undoubtedly fast, and the journey is just beginning.